Hi everyone, this is the topic of transformations, which is a topic for the International Baccalaureate course, Maths Standard. It's normally taught in Year 11, but I'm actually teaching it in Year 12 after we've done calculus and vectors. So we're going to go through a review of functions, and then we'll look at the three transformations, which are translations, stretches, and reflections, and then we're going to look at multiple transformations. So let's begin with a review of functions. For the function f of x equals x plus 1 on x, find the axes, intercepts, the turning points and determine their nature, the asymptotes, state the domain and range of the function, and sketch the function showing its features. Let's begin by finding the axes, intercepts. Remember, we find the y-intercept by substituting x equals 0. We find the x-intercepts by substituting y equals 0. So finding the y-intercept, we're going to substitute x equals 0, which means finding f of 0. Substituting our 0 in here is no problem, but here we're going to strike a problem. 1 divided by 0 doesn't exist, so therefore there are no solutions, no y-intercept. Now finding our x-intercepts, we solve f of x is equal to 0, because that's the same as putting 0 in for all of this. Let's just do a little bit of algebra. So I've substituted the 0 in. I'm going to bring this 1 on x over the other side. I've flipped it around at the same time. Now let's multiply both sides by x, gives us x squared is equal to negative 1. Square root of both sides, can't have the square root of a negative number, no solution. So there's no x-intercepts either. Now let's find the turning points and determine their nature. So that's going to involve solving the first derivative equals to 0. So we're going to take our first derivative. I've turned it into index form to make it easier to differentiate. When I find the derivative of x, that's 1, and the derivative of x to the negative 1 is negative 1 x to the negative 2. So 1 take away x to the negative 2. Now we want to solve that equal to 0. A couple of ways to do this, but I'm going to take this over the other side. I'm going to take that opportunity to turn it back into fraction form. Multiply both sides by x squared. Gives us x squared equals 1, and then solving that we get x is equal to plus or minus 1. So that's the x coordinates of the turning points, but we need to substitute back into the curve to figure out the y coordinates. So when I put plus 1 into here, I get 1 plus 1 is 2. When I put negative 1 into here, I get negative 1 take away 1, which is negative 2. And so our turning points are at 1, 2, and negative 1, negative 2. But we're not finished because we have to determine their nature. And the easiest way to do that is the second derivative test. So we had our first derivative, 1 minus x to the negative 2. Now we're going to do our second derivative. The 1 will go to 0. The negative 2 comes down, becomes positive 2, x to the negative 3. Now one by one we're going to substitute in our x coordinates into here, and then figure out whether they are maximums or minimums. So first one, f double dashed of 1. If I put that in there, I'm going to get positive 2. So 2 is greater than 0. Therefore, it is concave up. So it's a minimum. Now substitute in your negative 1. Putting negative 1 in there, I've got negative 1 all cubed on the denominator. That's minus 1 times minus 1 times minus 1, which is minus. So it's going to be negative 2. Is less than 0, therefore it's concave down, therefore it's a maximum. So 1, 2 is a minimum, and negative 1, negative 2 is a maximum. Let's move on to asymptotes. Now remember there are vertical and horizontal asymptotes. Let's begin with the vertical one. We're looking for any pronumerals on the denominator. There's one. Remember we can't have 0 on the denominator, so x equals 0 is an asymptote. Now for our horizontal asymptotes, we find the limit as x approaches infinity of this expression. We write it like this. Now this is a bit of a weird one. It's actually not a horizontal asymptote, which I'll show you in a second. But we want the limit as x approaches infinity of x plus 1 on x. Well, that part there is easy. That's just 0. So we can wipe him out. But what about this? The limit as x approaches infinity of x is infinity. So it actually doesn't have a numerical value for the limit, but it does have an upper bound. it never gets past x, which I'm going to show you on the graph in a sec. So the limit of this whole expression is x. State the domain and range of the function and sketch the function showing its features. I'm going to do the sketch first. So here we can see our vertical asymptote through x equals 0 and our diagonal asymptote y equals x. We have our maximum point, -1, -2, and our minimum point, 1, 2. And you can see how the curve never ever escapes this line. It's almost like it's being corralled. It gets closer and closer and closer to it, but never escapes it. When we come to do the domain, we know that it's not going to exist at x equals 0, but is it going to exist all the way to infinity? Because it looks like it's got a big hole here. So we're just going to follow this curve in our minds and think about whether every single number all the way to infinity is going to be possible. And it is. Okay, so it is going to exist. So the only problem we've got is that x equals 0. So we write x such that x is not equal to 0. The range is a little easier. We can see this great big hole. So we're talking the y values now. We can see this hole here. So we're going to write y is less than or equal to -2, or y is greater than or equal to 2. And there's our range. Okay, let's review limits as well, because they are something that students do have difficulty with. Let's recall that the limit as x approaches 2 of x plus 2 is the value of x plus 2 as x gets closer and closer and closer and closer to 2. What is its limit? What can't it go past? It's exactly the same as substituting it in. So 2 plus 2 is 4. So as I get closer and closer and closer and closer to 2, x plus 2 is going to approach 4. In this case here, we haven't got one that's quite so straightforward, because as x approaches 2, it kind of falls into a hole. X minus 2 is equal to 0, and if we actually got to 2, we're going to have a denominator of 0, which we can't have. So what we do to do this question is we try and cancel out the denominator, which we can do. We've got a function on top that we can factorise. So the top becomes x minus 2, x plus 2, and we can cancel out those x minus 2's. So it actually becomes identical to the top question. The limit as x approaches 2 of x plus 2 is 4. Now, as a graph, that actually looks like this. This function here looks like some sort of parabola thing, but it's not. It's actually just a straight line with a hole in it. Okay, it cannot equal 2. So as x is coming along here, or coming along here, getting closer and closer and closer and closer to 2, it is approaching 4, and that's actually the answer. And now limits to infinity. Recall that the limit as x approaches infinity of 1 over x is equal to 0. As x is becoming bigger and bigger and bigger and bigger and bigger down here, 1 over that number is getting smaller and smaller and smaller. If we actually ever did get to infinity, it would be equal to 0, because infinity doesn't go into anything, it's too big. Discuss the behaviour of the graphs below as x tends towards infinity. A, y is equal to 2 plus 1 on x. Okay, so the correct way to write this is to do the limit as x approaches infinity of 2 plus 1 on x. Now, as I just said before, this here is going to tend towards 0. So the limit of this whole function as x approaches infinity is going to be 2. What about this one? Let's write it in limit notation first of all, and then we're going to do something sneaky. So you may remember this from year 11, you might not. When we divide every single term, top and bottom, by the highest power of x, it's going to give us all of these sorts of things with all the x's on the bottom. That's what we want. So we either want numbers or x's on the bottom. It's no use to us having an x squared or an x. As I did the limit approaching infinity, I'm going to get infinity take infinity plus 1 over infinity take away infinity. So that doesn't make any sense to us. But this sort of method does. As x approaches infinity, that's 0, that's 0, that's 0. So we're left with 3 minus 0 plus 0, or 1 minus 0, which is 3. So the limit of this function here as x approaches infinity is 3. Okay, one more bit of revision before we move on to transformations. Find the points of intersection of the curves f of x equals x minus 1 in brackets x plus 2 in brackets and g of x equals 2x. So to find the points of intersection algebraically, we put those two curves equal to one another. Then I'm going to expand and simplify the left-hand side. Take our 2x over the other side, factorise and solve. Solutions are 2 and -1. Now remember, we want to find the x coordinates and the y coordinates, so I'm going to substitute these 2 points back into whichever curve is easiest, which is this one here. So for x is 2, g of 2 is equal to 4, and for x is equal to -1, g of -1 is equal to -2. So our points of intersection are 2, 4 and -1, -2. Okay, so now we're up to transformations. We can perform transformations on a graph to produce a related graph, and these include translations, stretches or compressions, which you might know as dilations, and reflections. Now recall that if we move a point or a shape through a transformation, the resulting point or shape is called the image. So this is actually called the pre-image, and then after we've reflected this over the x-axis, this is called the image. And what you'll notice is that the points retain the same letter, but they get an apostrophe. If we do multiple transformations, say we took this one and then reflected it over the y-axis, we would get a second apostrophe. So this point here, over here, would become B dash dash. Let's look at the different transformations. We'll begin with translations. We can translate a graph vertically. So if we're given y equals f of x, then y equals f of x plus b will translate a graph vertically by b units. Now if b is greater than 0, like in this case here, you can see b is equal to 1, then the graph is going to move up. If b is less than 0, then the graph will move down. We can also translate a graph horizontally. So given y equals f of x, then y equals f of x minus a will translate a graph horizontally by a units. Now this one can be a little bit confusing. They've done it this way so that if a is positive, it's going to move into the positive quadrant or the positive axis. So you can see these are positive numbers here. And that was exactly the same as the one we did previously. You know, if b was positive, then it moved it upwards. So we put it like that so that it will move this way. Another way to think about it is it moves to what makes 0. What makes 0 here? A. So this is moving from 0 to A, in this case to 1. So if A is greater than 0, the graph moves right. If A is less than 0, the graph moves left. Now translating a graph horizontally A units and vertically b units is the same as translating it by the vector ab. And this is going to result in the function y equals f of x minus a plus b. So let's have a look at an example. Given the function y equals 2e to the x, translate the graph y equals f of x by the vector 2, -3 to g of x. All right, so this y part here is easy. Okay, it's just going to go on the end. So it's going to be 2e to the x minus 3. This 2 here has to be subtracted from the x. So it's going to end up looking like this. G of x is 2e to the x minus 2 minus 3. You need to practice this a bit because this can be confusing. Here's our second transformation. We can stretch or compress a graph vertically or horizontally. So if we're given y equals f of x, then putting a constant out the front is going to stretch or compress the graph in relation to the x-axis. So here's our base graph here, y equals e to the x. If I put a number in front that is greater than 1, it's going to move the graph further away from the x-axis. If I put a number in front that is in between 0 and 1, it moves the graph closer to the x-axis. Now when you were learning this, you probably learnt that a number greater than 1 makes this steeper, and a number less than 1 will make it flatter. But we can also stretch or compress the graph horizontally, and that means that we're going to put the constant in here with the x rather than out the front. And that's going to stretch or compress the graph in relation to the y-axis. So you can see here is our base graph, when we put a number in here that's greater than 1, it's going to move the graph closer to the y-axis. And when we put a number in here that's in between 0 and 1, it moves the graph away from the y-axis. It's actually the same as the previous slide. So I wouldn't get too worried about this. Just remember that if I'm going to put a number that's greater than 1, it's going to make the graph steeper. And if I put a number that is in between 0 and 1, it's going to make the graph flatter. If you want to have a look at why that happens, let's take that top one, y equals the square root of 2x. And I'm going to split it into the square root of 2 times the square root of x. Can you see we've got a number constant out the front of the function, just like we had on the previous slide. And this number, square root of 2, is 1.4, so that is greater than 1. So effectively, it's the same rule. So don't get too worried about whether it's the x-axis or the y-axis. Just try and remember this simple rule. If it's greater than 1, it's going to make it steeper. If it's in between 0 and 1, it's going to make it flatter. The only exception to that is trig graphs, and I'm going to show you that a little bit later on. And here's our third transformation. We can reflect the graph over one of the axes. You're probably used to this one. Here we've got the line y equals e to the power of x. If I put a negative in front of the whole function, like here, it's going to reflect it over the x-axis. And if I put the negative in next to the x, like here, then it's going to reflect the graph over the y-axis. All right, let's have a look at multiple transformations. So obviously we can do multiples of those three things, the translation, the reflection, and the stretch or compress. So given the graph of y equals h of x, sketch the graph of y equals h of negative x plus 1. We're going to do this in 2 stages, and it doesn't really matter which order you do it in. So we could move this all up 1, and then what's this negative here going to do? It's going to reflect it about the y-axis. But I think the first one I've done, is to reflect it about the y-axis and then move it up 1. So there's the graph of y equals h of negative x plus 1. How about this one? Y equals negative h of x on 2. So this is going to compress the graph closer to the x-axis. But it actually makes sense. So don't worry too much about learning those rules about what does what. If you want half of hx, we want this whole thing halved. So instead of coming up to here, it's only going to go to 2.5. This part here is going to go down to 1. It's going to stop at 1. And this here is going to go halfway. So let's do that half first of all. So I've squished it in half. Now this negative means reflected over the x-axis, so we're just going to turn it over. And here's the last one, y equals h of x minus 1 plus 1. So we're going to move it to the right 1 position and up 1 position. So over 1 and then up 1. Okay, as promised, let's have a look at those transformations in relation to a trig graph like y equals sine x. So we've got 4 transformations here. We've got a 2, a 3, -1 and another -1. What's this one do? This is a stretch. It's actually a vertical stretch. We know that, don't we? And with trig curves, it's called the amplitude. It makes it twice as tall. This one here is a horizontal stretch. This compresses the graph. This one here is a translation. It's going to translate it 1 unit to the right. And this one here is a vertical translation. It's going to translate it 1 unit down. So trig graphs are a really good way of having a look at all the transformations. The only one I don't have there, of course, is the reflection. I would need a negative here or a negative in front of the x. All right, here's a past exam question. Let f of x equal x squared minus 4x minus 5. The diagram shows part of the graph of f of x. The function can be written in the form y equals x minus h all squared plus k. And remember, h and k are the coordinates of the vertex. Part A, write down the x-intercepts of the graph of f. X-intercepts occur when y equals 0. So I want to solve 0 equals x squared minus 4x minus 5. I factorised that put it equal to 0. Using the null factor law, our x-intercepts are at 5 and -1, but we should write them in point form like this. So they're 5, 0 and -1, 0. And let's just put those on the graph. B, find the equation of the axis of symmetry. Now you can use the formula x equals minus b on 2a, or you can just find the average of these 2 points. But either way, the axis of symmetry is x equals 2, and we'll put that in as well. C, part 1. Write down the value of h. Well, this is a really easy question, isn't it? Because we know that the vertex is going to occur on that axis of symmetry. So this is going to give us the x coordinate of the axis of symmetry, so that's just 2. And then finally find the value of k. You can go and complete the square of this, or you can substitute the 2 in there and then compare the 2 curves. It's pretty much the same maths anyway. I'm just going to complete the square. X squared minus 4x, halve it, square it. So half of 4 is 2, squared is 4. And I've just adjusted this. 4 minus 9 is -5. Okay, because we can't change the question. So there's my square there, x minus 2 all squared minus 9. So k is minus 9. And that's that point there. The graph of the second function g is obtained by a reflection of the graph of f in the y-axis, followed by a translation of -3, 6. Find the coordinates of the vertex of the graph of g. Alright, we actually only need to transform the point to -9. So a lot of students might have tried to transform this whole thing. You don't need to, you can be clever about it. So just this point here. So we're going to reflect it over the y-axis, and then we're going to transform it by this translation here. The reflection is going to become -2, 9. That's pretty easy. Now this translation, I'm going to go -2 minus 3 is -5, and then -9 plus 6 is -3. And so after it's been translated by the vector, the coordinates of the vertex of the graph of g are -5, -3.